All right, hello. So for this video, what we're going to be talking about is kind of the fundamentals of reporting values in this class. So we'll be talking about significant figures, uncertainty, how to report it, and what different types of uncertainty are. So the biggest thing you're going to be doing in this class is you're going to be taking a measurement. You'll have a measurement that you're going to record. And then you'll have plus or minus some uncertainty or error. So that's going to be the most important thing in this class. Every time you make a measurement, you're going to have a value, and then you're going to have some uncertainty in that value. So then the question becomes, how do you report this? So first thing we've got to talk about is significant figures. So first we're going to talk about significant figures. So please bear with me while I figure out how to use this kind of digital pad. My handwriting is poor, as you can already tell. So the first thing, we'll talk about significant figures. So I'll call those, in the future, I'll call those sig figs. And so the question becomes, what are significant figures? So let's say you have a value, and it's 12.527. We'll give it some units. We'll say centimeters. Everything in this class will have units associated with it. This is more important than if you're doing a theory class, and you don't have to worry about that sometimes. So let's say you have a value of 12.5. So the question is, how many significant figures is it? So some people might say it's 3 significant figures because there's 3 kind of digits here after the decimal point. In reality, there's 5 significant figures here because you're reporting 5 digits. So let's say you have an uncertainty on this value, like I wrote above, measurement plus or minus uncertainty, and you have an uncertainty. And we have an uncertainty of 0.152, also centimeters, let's say. You'll notice here I put a 0 in front of this decimal point. That's good practice to get into because if you left off the 0, if the decimal points can sometimes be small, and if they disappear, it might look like you have 152. So if you had 12.527 plus or minus 152 centimeters, that's going to be a big problem. So make sure you put a 0 before the decimal point. So then the question is, what do you do here? So you have 12.52 centimeters plus or minus 0.15. So the first rule we're going to learn in this class is you're going to round all error. So this is not the error or uncertainty. I'll use that kind of interchangeably. To 1 sig fig. So that's the first big rule we're going to learn about reporting values in this class. Is you're going to round all error to 1 sig fig. There are rules, there are cases where you could report more than 1 significant figure. If you read the textbook associated with this class, there's a PDF on my courses. He'll talk a little bit about how if your uncertainty starts with a 1, so as we do here, you could keep 2. And that's just because of the fact that the difference between 0.1 and 0.2 is like 100% change in error, so maybe you want to be a little bit more refined. I think it's easiest for right now just to keep it to 1 significant figure. You may have heard in the past to keep 2 at all times. And there are cases where that's acceptable. There are cases where you would have 3 or more significant figures. And we'll probably talk about that when we get to advanced lab. I think for right now, it's best to kind of sit with a simple solution, and then you can kind of build on that. It's like normal things in physics. You'll learn one rule that's simplified, and then you'll expand upon that in the future. So in this case, we would round this. And then the second rule that you're going to learn is you're going to match your value, your measurement, to the same decimal point as your error. So in this case, what you would have is you would have 12.5 plus or minus 0.2. And then I put the uncertainty outside of it. That's kind of a nice clean way to write it. So there you can see what we've done is we've rounded the error to 1 significant figure and then matched the measurement to that same decimal point. The reason for doing this is if your uncertainty is 0.152, you don't really know, you're unlikely to know the actual digits there. So these values here are complete nonsense. You don't know the value that well. So often what happens is when you calculate a value, let's say on a calculator, you have all these digits and you'll just report all of them. So you may have had in the past in classes where instructors told you, just give me 2 significant figures, so they'll give you like 2 decimal points or something. That was just so they didn't want you to report all these values on the calculator. In this class, it's a little bit more specific, so this is what you're going to want to do. And so there's a kind of the standard rule. And then you want to report it like this with the units on the outside. There's another case here. I'll just give you an example of how to do this with exponents. So let's say you had a value that was 10,000 volts, let's just say, plus or minus 5,000 volts. The question is, how do you report that? So these numbers are a little unwieldy because of the fact that they have these many orders of magnitude. So what you want to do here is actually, you would just report this as 1 plus or minus 0.5, and actually I already screwed up. This would be 1.0 plus or minus 0.5, and then you would put the exponent out here times 10 to the 4 volts. So here what you're doing is you're matching these and giving these the same exponent and putting that out here. I wouldn't write 1 times 10 to the 4 plus or minus 5 times 10 to the 3 volts, because it's kind of hard to see exactly where those are. 3 and 4 are kind of easy numbers to think about, but if you have much smaller, much larger numbers, that becomes a little bit more difficult. All right, so let me just zoom out for a little bit here before we move on. And so here, this is just about uncertainty and propagation and how to report significant figures. So the big thing is report error to 1 sig fig and then match measurement to each decimal point. And I'll post these PDFs online, so if you missed a line while we're writing through here, you can look at that. You can actually look at it while you watch this. That's fine as well. All right, in this class, what we're going to talk about are the fact that we have 2 types of error or uncertainty. I'll just write error here. So the one is a random error, and the second one is systematic error. So random error, and we'll use an example here of let's say like a bullseye. You have a plot here, and you expect the value that you're going to have is at the origin here. And so if you take a bunch of measurements, you'll find that you kind of get a scatter around that value. So the random error is the fact that you just get all these values, and every time you take a measurement, it's slightly different than the last time. And there's a bunch of reasons for that, and we'll talk about that, and you'll kind of learn what they are. So a systematic error is if you do the same experiment, and instead of you expect, let's say, this is more useful if you talk about what you expect. If you don't know what the value should be, it's actually very difficult to address systematic errors. But instead of having a bunch of data centered around where you kind of expect it to be, you have it offset by a little bit. So there's some kind of systematic error in your experiment that's causing all the values to be offset from the center. So these are really hard to analyze and address. So really what you have to do is make sure that you don't have systematic error in your system. This is like if you take a measurement. So in the first week of class, you'll measure the gravitational acceleration g, and let's say you measured a bunch of times and you're consistently getting above 10 instead of the expected 9.8. So there'd probably be some systematic error that's causing your measurement to be high. That is very specific to individual experiments, and how to address that will vary a lot. Random error is really the scatter around your true value. And what you're going to want to do is minimize that scatter as much as possible. That'll depend on the experiment. Let's say if you have a wire that's not shielded and you can have stray electric and magnetic fields that'll cause your signal to be different, that'll cause a larger scatter of random error. So if you take a shielded wire instead, you would get a smaller scatter. And so what you want to do is minimize both these things. In systematic error you want to minimize so that you're measuring something that's a true value, and random error you want to minimize because you don't want to have a large random error, because the larger your error is, the larger your uncertainty is, and you are less sure about the value you're measuring. So that's just a big one. Mostly in this class, when we're talking about error and uncertainty, what we are talking about is, in fact, the random error. There will be times that you have to address systematic errors, but again, that's very experiment dependent. All right, so for the next, kind of the final big thing for this section is something called propagation. of error or uncertainty. So this is the kind of thing, if you have a function that you're interested in, or a value that you have interest in that depends on another value, if you have uncertainty in x, what is the uncertainty in the value that you used x to find? And if you look at the book that we're using for this class, and I'll give you some problems out of it. Taylor, he has all these different rules for if it's addition, if it's multiplication, if it's a power law, how do you do this? And I find those not really useful because they're not shorthand, but there's actually one really kind of equation that rules it all. So I'm just going to teach you that. So the uncertainty in f, in this case, is the absolute value of the partial derivative of that function f with respect to x, the variable that you measured, times the uncertainty in x. And we put an absolute value there just because uncertainties are always reported as positive values because you have plus or minus the uncertainty. So you just throw some absolute value bars on there in case the partial derivative pops out a negative sign. And that's really it. It's really simple. If you have more than one piece measurement, so if you have f is a function of x, y, ... many different variables, you have a similar equation. So you do something called, you add them in quadrature, which you may have heard before. So the uncertainty in f is just the square root of the derivative of f with respect to x times the uncertainty in x squared plus the partial derivative of f with respect to y times the uncertainty in y squared. And then you just do that for as many variables as you have. And that's it. It's actually really simple. Sometimes these derivatives can be a little tough, and it just depends on the value, the function that you're evaluating. So again, let me zoom out a little bit here. The idea is if you have a function that you're interested in, a value that's a function of a bunch of other variables that you measured. So here you measure x, y, blah, blah, blah. You measure all those variables, and you use those to calculate another quantity that you're interested in. The question then becomes, what is the uncertainty in that quantity? So all you have to do is you just take a bunch of partial derivatives. And then you do something called add them in quadrature, which means square them, and then take the square root. That's why when we had a function of one variable up here, you just had absolute value signs. That's what the squaring and square root does. It just turns into an absolute value sign. And that's a big one that that big equation that you're gonna use a bunch in this course. There's a way to do this numerically with a computer using Excel or a spreadsheet or Python, and I'll show you how to do that in the future. But for now, just do it this way. You'll have to do this the very first lab. That's kind of the big takeaway. The last thing I'd like to talk about, just briefly, is something called fractional uncertainty or fractional error. And so what this is it's just saying the uncertainty of a value divided by the value itself. And this is kind of a percent error. This is super useful if you're trying to look at different things. There are versions of the previous equation. I'll scroll back up. There are versions of the previous equation that use fractional uncertainties instead. And that can be useful. But for now, if anyone ever asks you what a fractional error, it just means the uncertainty divided by the value itself. It's kind of saying how large is the uncertainty compared to the value. So if you had like 10 plus or minus 10, you have a 100% error, which is a problem. So usually that value should be under 10%. And you may find, just when you're interested in values and how good your reporting is and how good your measurements are, that's an interesting quantity to use. So what I've done is there's a sheet online on my courses for you to practice basically error propagation and significant figures a little bit, just so you get in practice. This is something that by the end of the course you'll be very good at.